All right, in this second part of 2.2, this is 2.2, number 2, we will talk about the limit which doesn't exist, the limits that don't exist, and what is called one-sided limits. What are one-sided limits? Well, they are precisely what you think they are. Okay, so I don't think it's going to be too difficult. Now, you have already seen the limit does not exist. Okay, DNE does not exist. Yes, you already have figured this out. You can write capital letters, lowercase letters, I don't care. The limit does not exist. Oh, this limit I'm talking about is this limit of f of x as x approaches a particular x value a. All right, this thing does not exist if f of x approaches different values from the two sides. Okay, now you have seen this before. Here's an example of a function that has no limit. Like here's that, and then this, you know, if you have a jump. Or possibly you may have an asymptote like this, right? Okay, so these cases, or maybe what happens is the function could do something very strange as it approaches a. It could like oscillate up and down, oscillate up and down, up and down. And if I know this is really hard to imagine, we will give you a specific example of these things. But these are cases. Let's give names here. A gap, infinity, and oscillation, infinite, closer and closer oscillation. If these things happen at A or close to A, then we say the limit, well, we know the limit can't exist by the definition we gave you, right? Okay, so here's an example of this. And by the way, in these cases, if they approach two different values, there is a way to define the left and right hand side limits, which is going to follow this example. But here's one cool example. It is so bad, some people call this the sin example. It's you see the word sin right there, right? The sin. Okay, this is a sine of 1 over x. Now think about what happens here as x approaches 0. Oh yeah, so the problem is find the limit of fx as x approaches 0. Right now, first of all, this is an odd function. So you can figure out what happens on the left-hand side if you know what happened on the right-hand side. Okay. As x approaches 0, which is what we are trying to figure out here, right? What's going to happen? 1 over x approaches infinity if x is approaching 0 from the positive side. Okay, so that would be this way. Because here, you know, x is approaching 0 from the positive side, so x will stay positive, even though it gets smaller and smaller. And then, I mean, think of numbers like 1 divided by 0.1, which is 10, 1 divided by 0.001, which is 100, and so on, right? So what is a sine of 10, sine of 100, sine of 1,000, sine of 10,000, sine of 1 million? Well, they just go back and forth, right? So it's just going to oscillate between 1 and -1 faster and faster as it goes like this, okay? And as x approaches 0 from the negative side, 1 over x approaches negative infinity, because these are numbers like 1 over negative 0.0001, which is, what is that? Negative 10,000, right? So it oscillates in both directions. So here's the very weird picture. And you can try to graph this on your graphing calculator. It really is cool. I wish I could show you that, but it's really a sort of cool looking thing, and you can keep zooming in and zooming in and zooming in, and it'll just not. It can't show you everything. Okay, so it gets faster and faster, and it just keeps going and going and going, and it never reaches 0, right? So because f is not defined at 0, but it's defined at every single point besides 0. And this side is the opposite. It gets closer and closer. It oscillates between 1 and -1. Okay, and you can tell what happens is as x approaches 0, it just keeps going back and forth, back and forth. It doesn't approach any particular y value. It just oscillates between 1 and -1. And same thing here. Okay, so we say the limit of sine of 1 over x as x approaches 0 does not exist. Okay, so this is a very cool and wild counterexample, which is one of my favorite. When you spend a lot of time with calculus, you start to recognize certain examples and counterexamples as your favorite, and that's good. Okay, you sort of own these examples, and that's what you want to. That's where you want to be. All right. So before we close this section, let's do one side. I have this, and then I have a related question, a related topic of the infinite limits. Okay. So one-sided limits. Okay. I think we can figure out what this is. All right. So here's an example, and maybe I don't have to give a precise definition if I do this. Let's say this is 2 and this is 1 and this point is a. Okay, and here's the function that has a big gap at 1 at a. Okay, I think you can understand that this limit as x approaches a from the positive side, which is denoted by this plus sign as a superscript, is equal to what? What do you think this is? It's 2. Okay, because that is what the y value is approaching as x approaches a from the right, and as x approaches a from the left, f of x is approaching 1, right? And so this is the right side limit. Some people call this the right hand limit, and then this is the left hand or left side limit. Okay, and I'm not going to even describe exactly or what these things mean. I think you can understand this is the plus direction. So when I say this, it's approach. So this means x is approaching a from the right, and when I write x approaches a minus, that means x is approaching a from the left, which means that x is always less than a. So maybe I should say that too. X is always greater than a here. X is also always greater or less than a as you approach a from the left. All right, and here's the fact. Maybe you can write this as a theorem if you like. But we say the limit, well, we should know the limit of f of x as x approaches a exists if and only if the left hand or left side limit and the right side limit both have to exist and is equal to L. I should have said this is equal to L. Okay, so the limit, the both-sided limit exists and it's equal to L if and only if the left-hand side limit, left hand or left side limit and right side limit are both equal to L. Right, and so that is another way to look at the two-sided limits. That's not too difficult, right? Okay, so what about case where the value of f of x goes to infinity? What about infinite limits? Okay, And again, I'm not going to elaborate on this because I think it's pretty intuitively easy to figure this out. But if you have this function like this, and let's say at this point A, the graph goes like this and like this. Or the graph goes like this, but this side is that way. Okay. Or what happens if, so I should have drawn these nicer maybe. Graph goes like this and both going down. All right, so here we say the limit of f of x as x approaches a is, how should I write this? Well, so what happens is it gets bigger and bigger, right? And more precisely, what happens is as x approaches a, right, f of x approaches infinity, meaning that any point, any bound m you try to set, f of x close to a will go over any given m you think of, right? So if you say, look, I want this m to be 100,000, okay? Can you come up with x so close to a so that f of x is above 100,000, okay? And if you can do that for any big m, then we say that the limit is infinite, okay? Or infinity. In this case, a positive infinity. And here is the opposite case where here's f, here's f, here's f. X approaches a is negative infinity because in both directions, as x approaches a from the right or left, you know, the f of x is going down to negative infinity, which means that it's going to go further down than any other any number you give, no matter how negative your number is. Okay, so that's the negative infinity as your limit, and here is a positive infinity as your limit. So over here, the middle one, I think you can agree that the limit does not exist. Okay, but you can talk about the right and left-handed or left-sided limits. Okay, so let's see this. If you're approaching this from the right, that's this way, the limit is negative infinity. And as you approach, as x approaches a from the negative side, which is over here, then it is positive infinity. Now, if it's positive infinity, you can put the positive sign here, or you can just not have anything, and that means the same thing. So these are called, referred to as infinite limits. We'll do a couple of exercises here relating to these things, but a couple of things I should mention here. Notice here, all of these involve vertical asymptote, right? And these things happen when the denominator is equal to 0 or gets up closer and closer to 0. If the denominator gets closer to 0 and the numerator does not, then that ratio, that fraction, tends to go to either positive or negative infinity. So that's when you see these negative or positive infinite limits. Vertical asymptotes are involved in all of these cases. The second thing is, remember what I said, these things like positive and negative infinity, these are actually not numbers. And so when we say the limit exists, we say the limit is 2 or 5 or some finite number. So in all of these cases, it's still okay to say these limits do not exist. If somebody says that, that's actually not wrong, okay? Even though I said that, which is different from these, right? But if the limit is infinite or negative infinity or positive infinity, then we could also say that those limits actually do not exist, and that would be a correct statement, even though we would want to distinguish, you know, the cases where the limit is positive infinity or negative infinity. All right, let's do a little practice. Let's try to find this. Find the limit of 1 over x minus 3 to the square power as x approaches 3. Okay, so how do you figure this out? Well, you can graph this one, right? Or you can start to think of, start thinking of numbers like x, let x be 3.1, 3.01, ... Okay, as what happens then is, this is your f of x. Okay. Think of 3.1 here, and then of course the difference is 0.1, and if you square that, it's 0.01. 1 divided by 0.01 is 100. Okay, and if you do this, that would be this minus 3 is 0.01, whose square is 0.0001, and 1 over that is 10,000. Okay, and so you can quickly see that f of x approaches infinity. What happens if x is approaching this from the negative side? That's like 2.9, 2.99, and so on. Okay, well, if you plug in 2.9 here, you get negative 0.1 here. But remember, when you square this, that becomes positive 100. And so this also approaches infinity. Okay, and in fact, this kind of analysis will help you graph this. Right? What's happening is when x is equal to 3, this thing is approaching infinity from both sides. Okay, and it is in fact symmetric with respect to that line x is equal to 3. Think of this graph here, which is like this, and you shift it 3 units to the right, and you get that. Okay, and so you can say the limit as x approaches 3 of this expression 1 over x minus 3 quantity square is infinity. Now again, it is okay to say it does not exist, but more precisely, you would want to say that the limit is positive infinity. It's not a finite number, so the limit technically does not exist, but be specific and say the infinite limit is positive infinity. All right, so what happens if you have a slightly different problem where you have the third power? Okay, well, so now I think you can see this. You can do the same kind of analysis you did here, 3.1, 3.01. These values will stay positive, and positive number cubed is still positive. It's going to be a very small positive number in the denominator. 1 divided by a very small positive number is going to give you a huge number. So the graph will go like that from the right. Okay, so you can say this. The limit as x approaches 3 from the positive side is infinity. But if you now plug in numbers like 2.9, 2.99, and so on, approaching 3 from the negative side, you can see that's going to be a very, it's going to be always a negative number, closer and closer to 0. If you cube a negative number, you still get a negative number. So 1 over a negative number close to 0 is going to give you a very, very negative number, like negative 10,000, negative million, and so on. So the graph will actually go down this way. Actually, what's happening when x is equal to 0? That's negative 1/9. It's around here, right? And so the graph will go like this. It actually never becomes 0, so 0 is the horizontal asymptote, right? So the x-axis, y is equal to 0, turns out to be the horizontal asymptote here. That's not relevant. Anyway, so this will be negative infinity. So you can say this limit does not exist. I mean, yes, these limits still don't exist, but the limit here does not exist, because one is positive infinity and the other is negative infinity. Okay, so you have some exercises, I think, you are assigned, and I hope you will learn more as you do your exercises in section 2.2.